dear students. In today's lecture, we will continue our discussion on the solar terrestrial physics, its origins, and various components or various pillars of solar terrestrial physics. So, in the last lecture, we have realized that this entire discussion, this entire course is designed to understand how Sun and Earth are dynamically coupled, how the solar forcing, how the solar prominences, or how the uh, plasma processes originating from the Sun affect the Earth. So, this entire course is fundamentally based on solar prominences, the space weather events, their influence, their impact, and how to uh, develop mechanism or models which can predict space weather events, etc. Right. So, since everything starts from the Sun, we have to understand various aspects related to the Sun itself. So, for the first few lectures, we will try to see Sun in a detailed way. We will look at various energy transfer mechanisms and various solar prominences, etc. Right. So, to begin with, Sun is a star which is the only star in our solar system and is one of the billions of stars in our galaxy. So, Sun is entirely made up of gases which are 70% hydrogen and 28% helium. So, Sun is primarily a nuclear fusion reactor which is powering the solar system with its energy in different forms. Okay. Now, what is important is Sun, of course, is primary source of energy, and the primary mode of energy that we receive from the Sun is in terms of light, the electromagnetic radiation or the light that we get. Okay. And apart from this, Sun also emits energy in the forms of particles. For example, particles as in extremely energetic particles, plasma, intercoupled with magnetic field, etc. But Sun is a main star in our solar system. Okay. Now, how big is the Sun? Sun is approximately, if you compare diameter to diameter, if you take the Earth's diameter to be something like 12,800 kilometers, Sun's diameter is approximately 100 to 110 times the diameter of the Earth. Okay. Or it is approximately 1.3 million times bigger than the Earth. So, this is approximate size of the Earth in comparison to the size of the Sun. And what else is seen in the picture is a solar flare and accompanied by a huge coronal mass ejection. So, this coronal mass ejection is just also referred to as ICME. This coronal mass ejection is a burst of energetic plasma into the interplanetary space. So, what is interplanetary space? Interplanetary space, which is the space which pervades the entire solar system, and most of the things like the interplanetary medium is the medium which is between the planets and which is highly influenced by the Sun. Sun illuminates everything in this interplanetary space. Sun's energy is coupled with everything that goes on in the planets, like the terrestrial planets or the Jovian planets. But so this coronal mass ejections is an outward plasma burst which may sometimes reach the Earth or may not reach the Earth. It depends on several other factors, but what also you see is the solar flare or this brightening near the coronal mass ejection, which is an enhancement in the spectral electromagnetic spectrum that we receive. Right. So, right now we can see that the sizes associated with this coronal mass ejections are huge, and they, of course, as they travel in the interplanetary space outward, they may diffuse or many things can happen. But still, if you put Earth, to comparison, they are too small. The size of the Earth is too small, right? So that means this energy, if at all, if it makes entry into the Earth's atmosphere, can influence many things in the Earth's atmosphere, can can disrupt a lot of things. So this goes back to our understanding of space weather. So space weather is essentially covering all these topics, right? Space weather refers to all those dynamical conditions in the near Earth space, which can be affected by whatever that happens on the sun. Now, this whatever essentially covers all the solar prominences, right? Now, what have we learned? We have seen sun is a star, and how big is the sun in comparison to or in reference to the Earth. Okay, so for comparison, you can put different planets for reference, and this is how it may look like. So all the planets put together are a tiny fraction of the solar mass. Okay, even the bigger planets. So how does the sun compare to the other stars? So there are other stars in our galaxy, in our Milky Way. The sun is one among those. Sun is there is a specific way in which you can characterize the stars, but will not go into the details of that characterization. We will just see how does the sun compare to other stars in the solar in the galaxy. Okay, now active star, of course, it is an active star. It's not a dead star. It is in its prime of its activity. Okay, so active stars may range in size. The size is basically the diameter. So the active stars range in size from supergiants to dwarfs. And if you put sun to perspective, sun is a dwarf of medium mass. So it is just right in the middle. Okay, and stars may vary from very bright supergiants to very dim dwarfs. Okay, even there, the sun seems to be sitting right in the middle, which is like a medium bright dwarf. And in terms of the temperature, the color temperature, stars range from very hot blue on the surface, which you call as the O class, and to cool red on the outside, which are the M class. And sun is in between yellow. Yellow, I mean, you see the sun in yellow color, right? So because that seems to be the maximum lambda max, where you get the radiations of 5800 Kelvin will eventually translate towards the wavelength, which is right in yellow. Okay, so in a sense, sun is a star which is 110 times the size of the Earth and in diameter. And then based on these things, so sun is a dwarf of medium mass, medium brightness, and it is in yellow color. Okay, then a few facts associated with the sun. So these facts are generally readily available anywhere, but we are going through these facts just to have some sort of continuity uh, or completeness to the discussion of what the sun is and how the solar, if you want to understand the solar prominences, you have to understand whatever that happens inside the sun. On the surface is the place where you see all these processes to be originating from, but it is not just the evolution or the origin of these processes is not just confined to the surface, rather it lies much deeper. So you have to have a comprehensive understanding about the sun as a whole. Only then you will be able to understand and appreciate the other things that we are going to talk about the sun. So that's why I'm going through this sun facts. Okay, so sun is a normal G2 star. The classification is G2V, which is one among more than 100 billion stars in our galaxy itself. Right, so it's not a huge, or it's not a very big star, or nor it is a dwarf of very small size. It is just a medium range star, which is very commonly found. So if you put the distribution of, let's say, size versus number, then it would be lying somewhere in between. Okay, so the diameter is 13,90,000 kilometers and approximately 100 times the diameter of the Earth. So, and mass is 1.2 10 to the power of 30 kg. 1.2 10 to the power of 30 kg. And for reference, it is 333,000 times the mass of the Earth. And temperature is, this is a very important number. You should always remember this number as well as this number, the mass and the temperature. So temperature is 5800 Kelvin. Sometimes we take it as 6000 Kelvin. Okay, this is the temperature of the surface. What is the surface? Surface, if you look in the evening, the disk that you see in the sky, that is the surface. Okay, and that is at a very low temperature in comparison to the temperature in the center or at the core, which is 15.6 lakh Kelvin. Or yeah, this is the temperature at the core. So you see the disk in yellow color. The temperature outside is approximately 6000 Kelvin, but there is a heat source. There is an energy source actually, where energy is created actually. Energy is created at the core, where the temperature is very, very large, 15.6 10 to the power of Kelvin. Okay. Now, this is very important because why the temperature outside is not so high, why the temperature inside is very high. Of course, this is where the energy is created, whatever. And then of all the processes, whatever that happen inside, the surface is heated to 5800 Kelvin. So it's just like, you have an oven and the center of the room, and the room is heated to an ambient temperature of, let's say, 20 or 30 degrees centigrade. But if you go to the oven itself, it may be at a very high temperature. The coil may be at very high temperature. It doesn't matter. But what you see, the ambient temperature is 30 degrees Celsius. So this heat source over this diameter, over the heat source, sending out the energy to the outermost surface, which you call as the photosphere, we will come to that, is able to heat the outermost layer of the sun to 6000 Kelvin. So, what is happening in between is going to be interesting. Core is where the energy is created, and the outermost layer, outermost region of the sun is what you can see with your naked eye sometimes in the evening, probably. Okay. So, and more importantly, sun contains 99.8% of the total mass of the solar system. You see, this is a very important fact. Sun contains more than 99.8% of the total mass of the solar system. Jupiter contains the rest of the 0.2% is remaining. Of that, much of the mass is concentrated in the concentrated in Jupiter. Okay. Now, what is it? What have we learned? We have learned the diameter is very, very 110 times larger. Mass is so many orders of magnitude larger than the mass of the Earth. Where are we putting referencing to the Earth's mass? Because that's where we live. So we have to compare everything with respect to the planet that we are living. Okay, and most of the mass is the solar system's mass is 99 is concentrated in the sun itself. And chemical composition, you look at this chemical composition, because hydrogen is the most dominant chemical species which is there on the sun. So sun is just a hot bubble of plasma which is internally powered by nuclear fusion and spreading out energy till the edges of the solar system. Okay, because whatever the plasma that is there, because of its pressure, it is pushing the plasma from the outside, from the interstellar medium to a certain extent. That's where the edges of the solar system can be identified. Right. Now, apart from hydrogen and helium, most of the naturally occurring elements also constitute to up to 0.1% of the solar mass, which 0.1% of this number is still a lot, right? So it's primarily hydrogen and helium. Now, interesting aspect is that it would be the nuclear astrophysics or certain areas of physics which will tell you how these naturally occurring elements came into existence on the sun, starting from the humble hydrogen and helium. Okay, but that's not relevant here. But most importantly, we have to understand, we have to have a visual perception for the sun. How big is it? How bright is it? And what are the temperatures that are associated with it? And then, of course, then the other aspects that we are going to talk about, right? Right. Now, if you look at the interior structure of the sun, what does it mean, interior structure? Because we have seen hydrogen and helium seems to be constituting 99% of the solar mass. Then this hydrogen and helium constituting this is a very generic chemical composition wherever you go, right? But internally, how does it look like? So if you put the r by r naught, so r is the distance, let's say 10 kilometers, reference to the the radius of the sun, r naught, then you will get a fraction. So 0.1% means 10% of the radius of the sun at 10% of the radius, 20%, 30%, 40%, 50, 60, and you go on 1.0 you'll get, where you are actually sitting on the surface of the sun. All right. So if you take, so you are traveling away from the center or from the core, and mass fraction is again a fraction. So let's say mass of one particular species with respect to the total mass. Okay. So what you see is, you'll realize that hydrogen's concentration increases as you move away from the center or from the core. Okay, like this. And helium's concentration will decrease initially and will reach a saturation as you move away from the center. So what does it mean? So hydrogen's concentration is increasing and helium's concentration is decreasing. So this supports the basic idea of the nuclear fusion, where hydrogen atoms are being fused to form higher atomic numbers. Right. So similarly, you also have an isotope of helium, which peaks somewhere at 30% or 0.3 times the radius of the sun. Okay. Now, this is how the mass is distributed inside the sun. So how do we know? We never been able to send any instrument inside the sun, right? So you should think. This is where you can start thinking. Even before you can, even before, when we talk about these basic facts, sun is very hot object. The temperatures outside the sun, 5800 Kelvin, are too high, and the temperature away from the sun will not decrease just like in troposphere, but it will increase to several millions of Kelvin. Okay. Now, what is the fundamental idea of temperature and how it slightly changes when you talk about the idea of temperature in a highly diffused gas? That and all is a different story. But visual perception simply tells you that sun is a hot object, very hot object. So it's not practical. It's impossible for you to send any man-made equipment or anything which can carry out the measurements and tell you that sun's mass is this much, or sun's diameter is this much, or sun's chemical composition is going to be like this. It's not possible, right? So you try to search, or you try to read how the masses of the stars are calculated, how the chemical composition of the stars can be understood, how the chemical compositions can be evaluated. How do we know that this is the chemical composition? So if I say this, you have to believe it, right? But how, there should be some methods, there should be some technique, there should be some scheme to get these numbers, right? So even the mass composition, etc. Right. Now, what have we learned so far? We have just seen the basic numbers about the sun. So radius is 100 times the radius of the earth. Mass is 10 to the power of 30 kg. Surface temperature is approximately 6000 Kelvin. Many times you will see that this is 5800 Kelvin. Somebody says 5500 Kelvin. Just remember, 6000 Kelvin can be used for all the simple calculations only if you are not explicitly given the value of the surface temperature of the sun. If in any problem, if it is given that 5500 Kelvin is the temperature which is supposed to be used, only then you use it. Otherwise, you just remember a round figure, which is 6000 Kelvin is the average temperature of the photosphere. So core temperature is 15.6 million Kelvin. Okay, 15 million Kelvin. Okay, and luminosity is 10 to the power of 26 watts. And solar day, this is where it starts becoming relevant for space weather, or even becoming interesting. This is where it gets interesting, actually. Solar day. So you define day as as the amount of time, let's say one revolution if it takes. Okay, sun's one complete revolution around itself. So sun revolves around itself. The solar system also revolves around the center of the galaxy. So many things are going on, but we would never feel all of those things. Earth is revolving around itself, right? So it takes 24 hours for the Earth to revolve around itself, right? And sun revolves around itself in different speeds. So solar day is 24.9 days or 25 days, for example, round figure, 25 days near the equator. So equator is rotating at a speed, and the poles, it is taking longer. It is taking nearly 30 days. So this is 25 and this is 30 days. So this idea is called as the differential rotation. So where different longitudes are completing 2 pi angular displacement in different times. Okay, so the angular velocity is different, right? So this is because of this differential rotation, all the solar prominences originate. That is the basic cause for the solar prominences, be it coronal mass ejections, be it solar flares, anything. All these processes originate because of the differential rotation. We will learn more about this differential rotation, right? These are the vital statistics. Okay. Now, like I said, energy is created in the core of the star because of the nuclear fusion. Okay. And this energy has to be transported outwards. Of course, it has to be transported outwards. And when it reaches the surface, whatever may be the process that is going on inside, the surface, as a result of the energy input that it is getting, gets heated to a particular temperature, which in this case is 5800 Kelvin. All right. So if you look at the now within the sun, interior sun, there are different modes of energy transport starting from the core up to the photosphere. So core is where the energy is created. So we will not discuss what is inside, because we will have to discuss some other processes which are not relevant at this point of time. Once the energy is created in the core when hydrogen is fused to form helium. This energy flows out from the core by the means of radiation through the radiative zone or through the radiative layer, and subsequently this energy is transported by the process of convection and in the convective layer, right? And the radiation from the surface reaches the photosphere, which is the portion of the sun that we actually see, right? So radiation travels from the core towards the outward towards the radiative zone and then convective zone, right? So the typical sizes of these layers, why do we call it as radiative layer? Because radiative transfer is energy is transported by the means of radiation, so which actually doesn't require a medium. So like I said in the last class, vacuum uh, energy transport best suited is radiation is the best suited in vacuum, right? So typical size of the core is typical radius of the core. Let's say if it is core, then it is 170,000 kilometers. And typical size of the radiative layer is of the order of 420,000 kilometers. And convective layer is small, of course, in comparison to this, almost up to 1/4 of the size of the radiative layer. Convective layer is 105,500 kilometers. Photosphere is, of course, the topmost layer of the sun, which is of the order of 450 kilometers. And chromosphere, corona they are basically outwards from the photosphere, or you can call it as the atmosphere of the sun. Okay. Now, it is very important to understand why radiative transfer is going on, why convection is going on here. Okay. So we will discuss all that in the next lecture. But for now, what we have learned in this lecture is we have understood the basic facts about the sun. Okay, basic numbers. These numbers are very important. And then we know that energy is created at the in the core, and this energy, the energy that is created, is being is transported outwards by different mechanisms: conduction, convection, and radiation. Okay, and then whatever may be the process, at the end, the solar surface is heated to 6000 Kelvin by these methods, by these processes. Okay, all right.